All right, let's just jump right in. Welcome to this explainer. Today, we're going on a real hands-on science project quest where we're going to unlock the secrets of magnetism. We're going to take a journey from the raging seas of ancient history straight to your very own kitchen table. We'll be exploring the invisible forces that literally shape our world. And I promise you, by the end of this, you're going to know exactly how to build a working magnetic compass using just some simple household materials.
So before we get our hands dirty, I gotta ask you a question. What in the world do ancient sailors navigating through a terrifying storm, that snapping pencil box sitting in your backpack, and a mechanical hawking frog toy all have in common? I know it sounds like the setup to a really strange joke, but the answer is actually this invisible, silent force that completely connects human history to our everyday objects. And that force, of course, is magnetism.
Okay, let's get into part one, the magic of magnets. Think about this. Thousands of years ago, ancient sailors literally didn't have GPS. If the stars were hidden by thick storm clouds, they were completely lost at sea. But they discovered these amazing naturally occurring magnets called lodestones, which actually helped them find their way. Over time, humanity figured out how to create our very own magnets from pieces of iron. And today, well, those artificial magnets are absolutely everywhere. They're keeping your purse snapped shut, they're securing that pencil box, and they're powering your favorite toys.
And because we figured out how to actually manufacture these artificial magnets, we can now create them for whatever specific job we need. We've got bar magnets for your basic science experiments, disc and cylindrical magnets, ring magnets, which by the way are amazing for making floating toys, spherical magnets, and of course the classic U-shaped magnet. We've basically adapted this invisible force into almost every shape imaginable just to fit our daily needs.
Moving right along to part two, testing magnetic materials.
So, let's take a look at the results from a quick material test. If we take a normal magnet and bring it close to, say, a wooden pencil, absolutely nothing happens. Bring it over to a rubber eraser, again, nothing. But when we bring it right near an iron sewing needle, snap. It pulls right to it. It's incredibly specific.
Which brings us to a super vital definition. Not everything is magnetic. Materials that are actually attracted towards a magnet are called magnetic materials. The real rock stars of this group are metals like iron, nickel, and cobalt. On the flip side, things like wood, plastic, glass, and rubber are non-magnetic. They just simply don't react to the magnetic field at all.
And that brings us to part three, invisible forces at play.
Now, there is basically a golden rule when it comes to magnets. Every single magnet has two poles, a north pole and a south pole. And they are very picky about who they hang out with. If you put a north pole near a south pole, so unlike poles, they attract and slam together. But if you try to push a north pole to a north pole or a south to a south, meaning like poles, they repel. They actively push each other away. You can literally feel the resistance right there in your hands.
All this pushing and pulling is powerful, but it kind of brings up a really great question for our science project. Can a magnet actually work through a solid barrier, like wood or plastic? Like, if you put something between the magnet and an iron object, does that invisible force just break?
And the answer is a resounding yes. The magnetic effect can absolutely pass straight through thin, non-magnetic materials. This means you can place a piece of cardboard, a plastic sheet, or even glass between a magnet and your compass needle, and the force totally still works. You can even drop a steel paperclip into a glass of water and drag it up the side and right out of the water using a magnet on the outside of the glass. You're moving the clip without ever getting your fingers or the magnet wet. How cool is that?
All right, here we go. Part 4. Build your own compass.
Okay, this is the main event. Let's actually build a vital survival tool using just a few things you probably have lying around the house right now. Here is your step-by-step blueprint. First, grab a regular iron sewing needle. Place it flat on a table. Take one pole of a bar magnet and stroke it right along the length of the needle. When you reach the end, lift the magnet up, bring it back to the start, and do it again. You're going to want to do this 30 to 40 times in the exact same direction. Believe it or not, you've now just turned that needle into a magnet. Next up, push that needle horizontally through a small piece of cork. And finally, set that cork floating in a glass bowl filled with water so it can rotate around freely.
Now, once the water settles down, something completely amazing happens. If you gently spin the cork, it will always stop and align itself in the exact same direction. No matter how many times you spin it, it comes to rest pointing north and south. But why? What exactly is pulling on our tiny homemade magnet? Here's the big reveal. A freely suspended magnet, just like our floating needle, always aligns north-south because our entire planet is basically acting like a massive, giant magnet. Your little sewing needle is actually detecting and interacting with the invisible magnetic field generated by the Earth itself. It's truly mind-blowing when you really stop and think about it.
And hey, you definitely aren't the first person to use this trick. Long before the modern compass in a neat little glass box was a widespread thing, ancient Indian navigators used this exact same scientific principle. They used a device called the Matsya Yantra. Basically, it was a magnetized, fish-shaped piece of iron that floated in a vessel of oil. It acted just like our cork and needle, allowing them to navigate the vast open ocean even when the stars were completely covered up.
Let's wrap things up with Part 5, Fun Magnetic Toy Challenges.
So, I've got 2 awesome hands-on challenges for you to try out at home using what we've learned today about the power of magnetic repulsion, that pushing force between like poles. First, look up the maglev train. It's a real-life train that literally floats on magnets to reduce friction, and I challenge you to see if you can build a small model of it. Or you could try making a hopping frog toy by gluing ring magnets to a ruler with alternating poles and then attaching another ring magnet to a paper frog on a plastic strip. You can make the frog magically hop right over the ruler as the like poles push it away. It is so much fun.
Well, we've covered a ton of ground today in this explainer, from the deep history of ancient lodestones all the way to turning a simple sewing needle into a compass guided by the planet itself. But before we go, I want to leave you with one final thought to ponder. If the Earth is a giant magnet pulling on your compass, where do you think its true magnetic poles are actually located? Are they exactly at the north and south geographic poles, or are they hiding somewhere else entirely? I'll let you investigate that one on your own. Thanks so much for joining me, and keep exploring.